Hi, physics students. I hope you guys are all keeping well. This is sort of the first trial of the video. You'll have to see if you like it. Before you get started, you have to make sure that you have downloaded or printed out the physics chapter 18, section 2 on resistors in series or in parallel. So our objectives for today are to calculate equivalent resistance for a circuit of resistors in series and find the current and potential difference across each resistor in the circuit. And we're going to do the same thing for resistors in parallel. There's two different ways to approach these two different circuits. First, we're going to start with the series, and then we're going to start with the parallel circuits. But right off the bat, your first question is, how are Christmas lights connected? Are they in series for the entire length? So if any of you have had the joy of decorating for Christmas and getting out Christmas lights from the year before, sometimes the entire strand isn't working. You'll have, say, a third of the strand that's out and 2/3 of the strand that are working. What happens is you have kind of like three sets of series lights. So if they're in series, if one light is burnt out, the rest of the lights go out. If they're in parallel, that isn't the case. If one light is out, the rest of the lights stay on. So in like long strands of Christmas lights, if one of the lights is burnt out, you have a part of the strand that's out, and those are all the lights that are wired in series with that light bulb, and the other two parts are wired in parallel. So Christmas lights have three parallel, usually, circuits with bulbs that are connected in series. And a series, as you can see, I've put the definition here. It describes two or more components of a circuit that provide a single path for a current. So there's only one way for the current to flow. And it's usually two resistors. We're going to focus this week on resistors, which can also be light bulbs. So on your second question, you have kind of this picture of your light bulb, of your battery with two light bulbs in series. And it's asking you to draw a circuit diagram for the image. Now we're going to draw light bulbs as resistors. So we're going to start with our positive terminal. It's going to come in here, and then we have our wires coming off. And then this is how I like to do it. And then you have your first battery here, which is your resistor. And then it comes around, and then we go into our second light here and comes back around, and you have the negative terminal of your battery. If we had a voltage, we would label this with some sort of potential difference, or and then these resistors would be labeled in ohms, okay, in our resistance. And that would be the diagram that corresponds to the lights that you're seeing. Now, there are some important things to understand about lights in series and kind of what we're looking at here. Because charge is conserved, what do we know about the amount of charge entering and exiting each bulb? If charge is conserved, the amount of charges, actual negative charges entering our circuit, our resistor, is going to equal the amount of charges that exit it. So, so we know that the amount of charge entering the light bulb equals the amount of charge leaving the light bulb in a given time period. Because there's only one pathway, the charge entering and exiting the first bulb equals the charge entering and exiting the second bulb. So you've got the same amount of charge entering and exiting each bulb in the same amount of time. So if charge is Q, and we know Q1 is equal to Q2, and our time interval is the same, we know that our current entering the entire circuit is the same. So I, for bulbs in series, for resistors in series, is constant. okay? So we know that I is the same for both of these resistors. Our current is the same going into each of these resistors that are in series. Okay, so the equivalent resistance in a series circuit is the sum of the circuit's resistance. So we're gonna derive this formula because what we know for sure right now is we're looking at this circuit we have with the two light bulbs. We know that the total voltage across this entire circuit is equal to the load of our potential differences. So we have our total potential difference is equal to the potential difference across resistor 1 plus the potential difference across resistor 2. Now we know from Ohm's law that delta V equals IR. Okay, so we substitute that in. I, our total current times our equivalent resistance is equal to the current through 1 times the resistance of 1 plus the current through 2 times the resistance of 2. Since we know that the current going in resistor 1 is equal to the current going in resistor 2, and that in turn is equal to our total current, we know that I1 and I2 are really IT, the total current. So we take out our total current IT. Since it's on both sides of the equation, we can divide it out, and we find that our equivalent resistance is equal to the resistance of 1 plus the resistance of 2. Therefore, equivalent resistance equals the total sum of individual resistances in series. So it doesn't matter how many of these resistances you have, they all add together if the bulbs are in series, and they come up with our total equivalent resistance is equal to R1 plus R2 plus R3 and so on, okay? So if you have light bulbs that all have the same equivalent resistance, if you say I have 35 light bulbs in a string of lights and their resistance is 1 ohm, you would have 35 ohms for that entire string. We're going to solve our first example problem now. This is problem number 4 in your example. Now, the thing to note about resistance of a series combination is that the equivalent resistance of a series combination of resistors is always greater than any individual resistance. So we know because we're adding it all up, our total resistance at the end, this number is going to be bigger than any of these individual numbers. Make sure it's level. Okay, number 4, example. A 9-volt battery is connected to 4 light bulbs of resistance 2, 4, 5, and 7 ohms. Find the equivalent resistance of and current in the circuit. Okay, so these bulbs are in series, so the first thing you're going to do is draw it out with your given information. So start with your battery, which has a positive terminal. I'm gonna start in with my first resistor, and I know I need to draw 4 resistors total. Okay, resistor number 4. And I'm gonna come back up and end at my negative battery terminal. Now the potential difference across my battery, delta V, is 9 volts. My first resistor is 2.0 ohms. My second resistor is 4.0 ohms. Third is 5 ohms. And my final is 7 ohms. Now, my first thing I need to do is I need to find the equivalent resistance. So I need to find REQ, and then after I find that, I need to find IT. So I know from our first previous formula that we just derived, REQ is equal to the addition of all of my resistors. So if I add all of these together, I get 18.0 ohms. Now I'm going to use this equivalent resistance because I know my total potential difference is equal to IT times my equivalent resistance. So using that information, I know my current is going to equal my total potential difference divided by my equivalent resistance, which is 9 volts divided by 18 ohms. My current is 0.50 amps because I have two significant figures. When we add, we usually go to the final place. So this is the answer to the example. At this point, I'm going to ask you to work problem 5, do parts A, B, and C. You're going to be asked to enter those values into this video platform as a way for me to check your progress. So now is the time to do that. Now, the next question, number 6, says to think about a string of Christmas lights. When one bulb is not working, what happens? You know that what happens is the rest of the bulbs in series with that bulb is burned out and they go off, and then you have that horrible headache of trying to figure out which bulb is burnt out. So a lot of times when I'm working with Christmas lights, I will be sort of frustrated that they're not all in parallel with each other, because that sure seems like it'd be a lot easier to figure out which of my lights isn't working. But the reason why people will bother at all with series lights is that resistors can be placed in series with a device that regulates current. Adding bulbs decreases the current in each bulb. Therefore, individual filaments do not need to withstand such high currents. In addition, each bulb individually has small resistance, but when added together, a larger resistance is possible. So when they add together, they have this larger resistance, which then reduces the amount of current that each bulb has to withstand individually.